Now that we know what acids and bases are, we can start to classify them into a few different ways. For the most part, we're going to use that Bronsted-Lowry definitions of acids and bases, where acids are proton donors, hydrogen donors, and bases are hydrogen acceptors, proton acceptors. So the first thing we want to be able to describe is how many different atoms make up that acid. So we have first binary acids. This is at the top of page 3 in your notes packet. Binary acids which contain 2 elements. And examples of binary acids are things like hydrochloric acid, hydrofluoric acid, hydrobromic acid, and hydroiodic acid. So those are all binary. They only have 2 elements in them. And those are really the only 4 that we have. Ternary acids are then going to contain 3 elements. That hydrogen with 2 others. So these are all going to be a polyatomic anion, a polyatomic negative ion from the back side of the table. And the examples of these that we have here on our notes packet: sulfuric acid, carbonic acid, phosphoric acid, nitric acid, and acetic acid. I got a lot of stuff pre-printed on the slides for this video, so I encourage you at any point to pause the video so you can record, you can write down everything here that I have, and then keep going. So acetic anhydrides, that's our next idea. Acetic anhydrides are sort of a special class of acid. They are oxides of nonmetals which will produce an acid when dissolved in water. They are sort of it's sort of like if you've taken an acid and you take the water out of them, you get an acetic anhydride, which the name implies. It's an acid without water. Examples of these are SO2, SO3, NO2, and let's scroll down here just a little tiny bit. There it is, CO2, carbon dioxide. So these 4 examples, sulfur dioxide, sulfur trioxide, nitrogen dioxide, and carbon dioxide, they all can combine with water to form an acid. So I get H2SO3 here, sulfuric acid here, nitric and nitrous acid over here. So these are all combining with water to give us an acid, which, if you take a look at what these 4 compounds are, they are very major components in smog or in a lot of industrial processes. When we burn fuel, a lot of fuels, obviously we're producing carbon dioxide, but a lot of fuels have a little bit of trace amount of sulfur in them, which kick out these gases. And then, of course, 76% of our air is nitrogen, so we get some NO2 that shows up as well. The problem with that is, as those are in the atmosphere, we also have a lot of water in the atmosphere, and we get what we call acid rain. Acid rain, which is mainly caused, it's mainly caused by sulfur oxides and nitrogen oxides in the air, which combine with water, and they produce those acids in the air. The acids can then rain down and react with anything that acids react with, which, if you look back at your page 1, we said metals is a big one, but also a lot of things like limestone, marble, statues, a lot of buildings have components that do react slowly, but over a very long period of time, significantly, with acid. There is a demo that you're missing, that you're not in class today, the acid rain burettes, and what we look at is the idea that if we have in northern Wisconsin, there's a lot of granite. In southern Wisconsin, we have a lot more sort of limestone, and the gases in our atmosphere, as the acid rain rains down, it reacts with limestone, but it doesn't react with granite. And so even though we have more industrialized processes down in the southern part of our state, we have up in the air, there's a little bit more, let's go in black, there's a little bit more acidic rain in the southern half of the state, but as it falls, it reacts with the limestone, is actually neutralized. So in the northern part of the state, where there's a lot of granite, it doesn't react quite as much, and there's actually a little bit more problem with acid rain up there, because then that can harm plants and wildlife and accumulate in rivers and streams and make bodies of water much, much more acidic than they otherwise would be which then can have hurt the wildlife up there. So just like we have acid anhydrides, we also have basic anhydrides, and these are oxides of metals which will produce a base when dissolved in water. So examples of these might be potassium oxide, K2O is a solid, put that in, and we get H2O, or plus liquid. We get KOH, which would then be aqueous, or we might have something like calcium oxide, CaO, solid, plus H2O, liquid, reacts to form calcium, Ca hydroxide, OH2, aqueous. So those would both be examples of basic anhydrides. So you might have noticed here on a basic anhydrides, our examples are both metals. On the other one, the the acid anhydrides, we have nonmetals. Why is that? Well, on the top of your next page there, page 4 in the notes packet, metals tend to form bases. So we have a lot of metal, or bases have a metal in them. And that is because metals have less attraction for electrons. So the electrons are further from that metal, closer to hydrogen. Thus, the hydrogen is held more tightly to the metals than it is, or than the metal is to that bond. The flip side of this, of course, is then nonmetals tend to form acids, and it's going to be for the opposite reason. Please do pause here and go back and write that down if you haven't got it already. Nonmetals have a greater attraction for electrons. Electrons are closer to that nonmetal, further from the hydrogen. Thus, the hydrogen is held less tightly and can be dissociated from that compound much, much more easily. So they are then more acidic. There are substances that are actually right in the middle. They're not quite acidic, they're not quite basic, or more accurately, they are both. And those are amphoteric substances. Amphoteric substances can act as either an acid or a base. So if there is something that can accept or donate protons, it could do either. We call it amphoteric. So it can act as an acid or it can act as a base, and it really depends on what it is with. So water is a really great example of this. In this example, I have HCl, which is an acid, reacting with water. Well, since HCl is an acid, water must be my base. But I know that I can also react water with ammonium. And ammonium is a base, which means in this example, water must be an acid. So water, it's amphoteric. It can react. It can be either an acid or a base. Since we labeled those, let's label the conjugates on the right side. So HCl is an acid, which means that Cl minus is its conjugate base, and H2O is a base, which means that the hydronium ion is the conjugate acid. NH3 is my base, so ammonium is my conjugate acid, and water is an acid, which means hydroxide is my conjugate base. The last piece that we're going to add in for today is what happens when we combine an acid and a base together. An acid plus a base, if you, let's see, I'm flipping to the next page, you're not, is what is called a neutralization reaction. We know from the first page the properties of acids, they neutralize bases, and bases neutralize acids. So if we have an acid and a base, they neutralize each other, and the neutral compound that they form is water. They also form a salt, and the chemistry definition of a salt is not the same definition that almost everyone has. If you say salt, everyone thinks of sodium chloride and only that specific salt. In chemistry, a salt is any compound that is a positive metal ion plus a negative non-metal ion. And that includes all of our polyatomics. So when we learned how to name compounds back in mid-first semester, and there's about 4,000 different compounds or so that you know how to name based on that ionic naming structure, every single one of those is a salt. So an acid plus a base forms a salt plus water. And this is what we used for our definition for our copper chloride in our lab last time, where we had the parent acid and parent base, and we called copper chloride a salt because copper chloride is a positive metal ion and a negative metal ion. So what we need to do is we need to figure out what's actually made when we react these together. We know every single one of these is going to form water. Every neutralization reaction forms water. What's the other part? Well, I know that the acid and the hydroxide, let's do that in red. The acid and the hydroxide are going to form water. Acid, hydroxide, acid, hydroxide. So what's left? Well, the positive half is going to come from my base. So in this first one, I'm going to get magnesium, and sulfuric comes from sulfate. So that's going to get magnesium sulfate. Hydrobromic acid plus potassium hydroxide is going to give me potassium bromide. And acetic acid plus strontium hydroxide is going to give me strontium acetate. So we can write these in words, or we can also write them, of course, in our balanced chemical equations. So down here on the bottom, again, we know every single one of these is going to form a salt and water. So to make sure that I always remember, that it forms water, I typically do that first. So I say something plus water. It's a neutralization reaction. Acid plus base, salt plus water. Salt plus water. So what acid does it make? Well, if the acid and the hydroxide made my water, what's left? Sodium and hydrochloric comes from chloride. So this one is going to be sodium chloride, and phosphoric acid plus calcium hydroxide is going to give me calcium phosphate. So then to write these back, we need to go back and remember those all those acids and bases that we asked you to memorize first semester, and then the ones we just wrote on the front page of our note packet. You need to know all of those. So I know hydrochloric acid is HCl, aqueous, plus sodium, that's an Na. Hydroxide is OH. Sodium's a +1, hydroxide's a -1, so it's 1 to 1. Same thing over here. H is +1, Cl is a -1. So that's also aqueous. Reacts to form sodium chloride, Na +1, Cl -1, so that's 1 to 1. That is soluble plus water, H2O, which is going to be a liquid. That one's already balanced for us, so let's move on to the next one. Phosphoric acid. Phosphoric acid is hydrogen phosphate. So hydrogen phosphate, hydrogen's a +1, phosphate's a -3, so that's going to be H3PO4, aqueous, plus calcium, calcium Ca, hydroxide OH. I know hydroxide's a -1, calcium's a +2, so that's going to be aqueous as well. Oh, hang on, that wasn't the so. So it's CaOH2, there we go, and it's aqueous as well, forming calcium phosphate. Calcium with a +2, phosphate PO4 is a -3, so I need three calciums and 2 phosphates, aqueous plus water, H2O, liquid. So I can write from any acid-base reaction, neutralization reaction, I can write the products based on it's always going to form water, and the salt. The positive always comes from the base, and the negative half always comes from the acid, and then you need to reword them and put the correct suffixes on them so that they have their proper names, just like we've been doing all year. So you have a worksheet that is due on Friday. Please use all this to do the worksheet and ask questions ASAP if you